Good morning to all. In this video, we continue with the Flash Controller IP design. This is part C. In earlier two videos, part B and the initial one, you can refer for the more details what we are doing here. And in today's video, we are going to elaborate the kind of code written for this Flash Controller IP and try to simulate on a VCS. So start with this. So the simulation based on the VCS tool. So please refer my EDA tool tutorials regarding the VCS tool, and we are following the same folder structure and the make file and the file list for the simulation here. So it is better to have a look EDA tools tutorial for VCS tool before going into this video. So in last video we create a table related to the read commands. So for the readiness, I just add this slide for you. From this we can conclude the command is always in SPI mode, and address may be having the 24 clocks, 12 clocks or 6 clocks depending on the what mode of address we are using. Like SPI, if it is SPI, it is 24 bit or 24 clocks. If it is dual, the 12 clocks, and if it is chord, it is 6 clocks only. As well as there is a dummy, maybe 0, 8, 4, like that. Also data out, maybe 8 clock bit. 8 clock means we get the output on the SO pin, but if it is dual, within 4 clocks we get the data. If it is chord, we get the data on only 2 clocks. So these are the possible summaries. Address may be SPI, dual, chord, dummy may be 0, 4, 8, data out maybe 8 clock, 4 clocks or 2 clock required, like that, depending on the what kind of the mode we are using, SPI, dual or chord. So please subscribe my channel, make shares and make comment for any query, and support me. Thank you. So moving back to the architecture, we already saw this kind of diagram earlier. So for the sake of revision, like I just put this slide in this video. We have to provide the command address, data length for the transmit, data length for receive, status data, and the send buffer, maybe the n depending on the requirement, how much data you want to send. Also we get the receive data buffer, busy, start, reset clock, and we have the chip select, S clock, and these are the pins SI, SO, WP, SIO3, like that. So there are two models we have to concentrate it, command map and the CDD. CD means command data transmit receive, and whole is wrap up on the top, and there is one model from the Flash, or you can use a vendor based IP. Okay, so file details are there. We are referring the MX250 model. Okay, so command list is given in define in .vh, and it has all the defined files. All defined files, all the command defined there. Okay, and CD TXRX, it is a TXRX model, and this SPI dual and chord SPI, it is a command map. You can see what kind of things inside this. Always there will be the top and the test bench. There are some certain data files I am using for the storage purpose, and the same we are trying to read. So for the check, we can see what we are storing and what we are having that. Okay, for the verification. Okay, so the folder structure is the same that we are using for the VCS. So there will be one code folder where all the source file located, VCS folder where the make file is there, and the all files.txt is a file list. So command is simple: make top equals to the top of the test bench name and mode, whether it is RTL or synth. So we are going for the RTL only right now. Later on we see how much we have to left with the synth. So moving back to our terminal. So we are code ls. So these are the files we are talking about. So first we see the command list. Okay, we can check the mx. This is a model file from the vendor website. Okay, it will be a large file, so there is no point to have to discuss on this. Okay, but one more point is there. We are adding that hex files that I told to you. Okay, this is manually created file, so you can refer this for any alteration of the data. Main pins are this one. Okay, so just remember this. So if we are checking the model file, so obviously we can check the data file, one of the data files. Okay, for the sake of simplicity, what it contains. It is containing 0 at the start. It is containing 0 to 0 1 2 3 4 3 1f 0 5 0 6 0 7 0 8. Actually this much of data we are trying to read. Okay, so just keep in mind these numbers, and it is located at 10000. Okay, obviously it is a place somewhere in this model file where we are storing this data. Okay, so moving back to the command list, then this is command list. Okay, so it is the exact copy of the this command set actually. Okay, read command 03 value. There are 3 addresses like that. Fast read 0b. So we are trying to simulate up to this. Okay, for the read process. So this is the exact copy written in this. Okay, so obviously there are other commands there, but in this video we are trying to read the flash, so we are very much concerned about the reading commands. Anyway, you can have a look. It is a complete replica of that instruction set or command list in from the datasheet. So moving back to the command map, so we can check that. So as I already told that it will include the command list defined files here. These are the inputs. It is the exact map of the what we seen in the architecture. Okay, this one, this side, and these are the output, which is exact map of this side, output side. Okay, so what it actually builds, it is check the command code there is a one complete case statement here, very long case statement here, and each case atom is nothing but the code of that particular from the data sheet actually. Okay, 03, in that we have to send the 4 bytes, so the send count output will be 4 byte, means length of sending data is 4, and if we are sending additional of this, so there will be the data length plus. So in this read command we are not sending anything to the flash, so it will be the 4 plus 0, and we are receiving some data. So how much data we are required to receive, like that count is in this data length Rx. So I am trying to read almost 8 to 9 bytes, so this count will be 9. So send buffer will accumulate concatenation of the read command data, that is our 03, and the address in the test bench I keep the address 1000. So we are trying to read from that location. It is of 24 bits, so total is 4 bytes. So send count is 4, and it is in SPI mode, so this SPI dual mode is squad mode is 0. There is no dummy in this command, and there is no differentiation between the addresses, whether we are sending address in SPI, dual or quad. So 0 means SPI, 1 means dual, 2 means quad. So you can refer this here. So this is a command, 8-bit command, 24-bit address, and there is no dummy. We are getting the output from the SO pin. So all in SPI mode. So there is no much detail here. Let's say for sake of explanation, I goes to the, let's say fast rate, the command is 0b. So in that case there is a one additional dummy we are seeing this in this chart. So this is a command, 8-bit, address is 24-bit, and one dummy 8 clocks is there. So what this case statement is reflected, only the change we seen here in this count, it is of 5 bytes. 5 bytes means first is command, then 3 bytes from the address, 1 byte for the dummy. So in earlier dummy is 0, now we have dummy, so there will be the indication of dummy is there 1, and everything is in SPI. So these are the changes. Accordingly we can see, let's say anything else more than, yes, we can refer the EB command. This is a fast read quad IO. So in this 7 bytes we are sending, first is command, then 3 bytes for the address and 3 bytes for the dummy. So total is 3 plus 3, 6, and 1 byte for the command. So 7 bytes we are sending. We are not sending anything excluding this, so it is 0, and we are trying to receive some data from that particular location. So obviously the location I am kept the same, 1000. So, and it is in, you can also check the table as well. So SPI command is there. Okay, EB, and we are sending the address on quad mode. So the SPI dual quad equals to 2. Okay, and obviously there is a dummy, so dummy will be indicated by dummy signal, and address we are sending is 0. So obviously we are not we are clubbing this dummy and the address mode to define whether we are sending address by SPI or dual or chord. So we will see how we can club these two for the address mode in CD TXRX mode, TXRX module actually. So similarly you can go through this complete file. Okay, this was 6B EB. So up to this much we are trying to simulate because we are targeting the read side of Flash. So hopefully you can pause this video and check for the details. Okay, so moving back to this okay, now to simulate this we need to check all these details in the VCS terminal or terminal. Okay, and more important file is our CDTXRX, so we must go through that. So as we see from the block diagram, there will be the clock, reset, start and busy. Okay, and obviously there is an input from this this is CD TXRX. So these are the inputs coming from the external and these are the outputs to Flash. Okay, this side. So these are the inputs we can see in this side. Data send count, then buffer, receive count, then receive buffer, then dual chord, SPI dual chord mode, that is 2 bits. These are the pins which is referring to this this side. DQ IO 4 pins, then QI is an input 4 pins, and there will be the dummy and address. So it is reflected in the bottom side of this dummy input and address. Okay, so from this there is a one signal or wire we are considering which defines how much bits in parallel, either 1 bit, 2 bit or 4 bit, depending on the signal. We can say the SPI dual chord mode signal. Actually if it is 2, then we are sending 4 bits at a time. If it is 1, we are sending 2 bits at a time. If there is no 1 and 2, then it means it is 0. So we are sending the data on single bit or single pin. So it is a final state machine, so obviously we have to define this much of states: idle, command, address, dummy, data, receive. Okay, so from the data count we are trying to collect some numbers like address length, how much address length will be there, because there is a commands where sometimes address will be present, sometimes address will be not there. So from the chart you can get the things clear. From the chart we can see there are some certain commands where the address is presented. Okay, but there are some certain commands device related or something else, but only the command is there, there is no address is there. So that is why here we are calculating the address length, whether it is 24 or 0. Okay, so if data send out count greater than 1, it means there will be the command and address or something else. So obviously the address length will be either 0 or 24. So dummy length, obviously if the data count greater than 4 and the dummy is there, so obviously there will be the dummy cycles will be there. So how much dummy cycle will be there, either 0, 4 or 8, like that. So data length, obviously the earlier some count, like if it is 4 then command, then address and dummy. Depending on the count value, we are minusing that much of length and we get the how much data length we have to send. Okay, and for debug purpose I'm just add one register there, debug tx data. So whatever we are sending we get on this bus, so to cross check whether we are sending the same data or not, because in bit banking analysis we are not very much clear what we are sending and receiving. So we, to clarify that what we are sending, we can get the 8-bit data at debug tx data. So from this values data send count, we are very much interested to find the where the command bit started, end command value, then starting of address, then end of address. We are calculating the position of the command start, address start, dummy start, data start, so that from the buffer we can extract that and we can send that. So these are our output pins, 4 output pins, and it kept either the data of DQ or it will be in Z impedance state depending on the output signal OE. Okay, so there is a one signal which defines whether that pins are sending some data or it is in Z impedance state. So moving back to the final state machines, so it is a positive edge clock. At the reset we are kept the state in ideal condition, and this is S means chip select. We are deactivate the chip. BZ is 0, output is also 0, so all the states are Z impedance, all the states of the DQ pins is Z impedance. Then bit count, then byte count, and dummy cycles are 0. So these are the reset conditions, so that much we have to consider. If there is no reset is there, we begin with the case statement of the state machine. In the ideal case, these are the defined conditions we already seen there. But if there is a start signal is there, we start with the command. The next state will be the start, and we are indicated by the busy signal, and initially the bit count is 0, and all the pins we let to goes to the ground or 0. At the start of the command cycle or command state, we kept the chip select low, so we are starting the signaling towards the flash. So output enables means this DQ/IO pins now sending the data from the DQ. Okay, so we are sending the command. We already know that every command is in SPI mode, so we are sending only on the DQ0 pin, other pins are zeros. So the start of the command and bit count initially 0, so we are gradually increment this count one by one, and we are sending the data from this data set buffer from the start of the command position. So up to the 8 clock we are sending the one by one bit from this data send buff to the DQ, and which is gradually sending on the SI pin of the flash. So at the end of this bit count goes to the 7, which is our 8 clock. We check either we have to move to the address or we have to go to the idle state. If that command has address values, it means the data send is not equal to 1 or data receive is not equal to 0 or dummy is there. so we are not moving back to the ideal case. Okay, so in else part, so in the else part, if there is an address present there, then we switch to our state to the yes address, and the bit count goes to the 0. So in the address state, we enable the output, which is actually already enabled in the earlier stage, and the bit count goes less than 24 bits. So we check whether we club this, or we can concatenate address mode as well as the dual SPI dual chord mode pins as a concatenation, whether it is 2, 1 or 0 default. So if it is 2, then we are sending the 4 bits at a time. Okay, if it is 1, we are sending 2, means this is our chord, this is our dual, this is a SPI mode. Okay, and we gradually increment the bit count accordingly. Here is 4, 2 or 1. So at the end of this if statement, okay, we check whether there is a dummy or not. If there is a dummy, we switch to state to the dummy, and dummy cycle goes to 0. If there is no dummy but the receive count is greater than 0, so we goes to the receive state. Okay, at default we goes to the dummy. So in dummy state, we are check the dummy length, maybe 0, 8 or 4, like that, because initially dummy cycle is 0. So it might happen that the dummy also we need to send on the chord, dual or SPI. So using these two signals, we are defining how we send the dummy. Okay, either 4 clocks, 2 clocks wise, or 1 bit clockwise. So after that we are checking, also we are updating the dummy cycles. In the next phase or after some clocks, this if statement will false, and we goes to this. If the receive count is greater than 0, it means we are very much interested to either read process or write process. So right now we are implementing the RX, so we are also check the conditions that bit count equals to either 9 bit or 8 bit or 7 bit. Okay, we'll check whether how we can estimate this. Okay, so there are some certain commands, like if the data command is 3B, 6B, so the bit count should be 9. If the data is 0B or something else, we have to keep the bit count is 8 or 7. So at the last we are goes to the ideal case, if there is no receive count or no data to be received. So we back to the ideal case. At the receive side, what we are doing actually, we are make all the pins of the flash output equal to Z impedance strength, and then we are checking the bit count whether it is above the required bits per clock or not. So these are the conditions we have to check, because this bit count we are gradually decrementing that, okay, according to the 1 bit, 2 bit or 4 bit. So in else part, if we have to in state receive, we have to check this part also, because we are reading the data at the falling edge of the clock. So this is separate always block, where the negative edge clock is detected, and these are the reset conditions. If we are in receive state and we check whether it is a SPI, dual or quad. Accordingly, we pick the data from the QI, which is our input site. Okay, from this block diagram, this is a QI, and we take these 4 inputs to concattenate with the receive shift register. Okay, with the either in 4 bits or 2 bits or 1 bit. So at the false of this if condition, we move this shift register receive data to the receive buffer and increment the byte count. Okay, so this will be continuous until the byte count is less than the receive count, which is defined by the host, and if it is goes to that level, we back to the idle state and make the chip select deactive. Otherwise, we again load with the bit count 7 and receive shift register equal to 0. So gradually we are incrementing, or we are receiving the data from the flash up to this byte count greater than equal to defined receive count. These are the basic code we are written for the command data receive transmit receive. So for sake of simplicity, I just slowly scroll down, so you can pause the video and you can notify or record that things. Okay, so please subscribe my channel, share the video to your colleagues, and support me. Okay, okay, moving back to the top. Actually, top is nothing but our same architecture diagram arrangement. Okay, exactly we are mapping these things into this top. These are the inputs. These are the also inputs, command address, length of TXRX data. Okay, so these are the receive buffer. This is our command map module. This is our CDTX module. DQ bus assigned to this SISO WP SIO3. This is our model. So obviously it is not a complicated top. Actually, we can go with the test bench. So in test bench, obviously there is a clock, reset, start, and these are the register address. Okay, so clock is generated here, instance of the top, and I'm creating one log file for the record all these things. This is a reset. These are the initial conditions. First command is our read command. Address we are keeping, as we know that we are reading from 100000. There is no data to send, so the TX length is 0. We are trying to read up to 8 bytes from that location, and we are placing start command. We are waiting for the busy to be released, and after that we are trying to read the data from the receive buffer. Okay, so this is for the read command. After the read command, we are going to for the fast read, that is command 0b. We place the start here because already we are already kept these things, address and the length and receipt length is same, so we are not altering anything there. So in this we are just place the start and wait for the busy to be ready. Okay, again we are looping back the receive buffer for the 8 bytes. So then read command bb, same things we place here. Okay, copy paste we can do for all the commands, bb, then 3b, then quad read command 6b, then what is it, w4 read, that is e7h command, then at last what the command is, okay, this is the last command I think. Okay, so the last command is 4 read, that is eb. So we can check with the simulation. Okay, so we need to go to the cd vcs, and one more thing, we have to check the make file and the all list .txt, that is our file list. So we can check the file list first. This is our file list. These are the files we need to read. Okay, others are commented from the earlier video. Okay, so this is our file list. Again we need to check a make file. So the make file is the same that we are doing from the last videos actually, but still I am just scrolling it for you. So we are very much interested in simulation with the RTL. If it is synthesis based, so synth 90 means 90 nanometer, synth 45 nanometer. Okay, so sorry for the very large video, it is goes to the up to 40 minutes, but these are the required things to recall. So the command is make top equals to tb QSPI, sorry, tb QSPI, then top, then mode equal to RTL. So it will pop up a DV panel. Okay, actually I already have the last restored session. So because time is already goes to above 40 minutes, so I just simulate it. You can just press F5. We got the result, but still we need to go through all the signals, because it is already 14 minutes over here. So it is better to discuss this waveform in next video along with the device related commands simulation. Okay, so but you got the point, I hope you got the point. One more thing to check Okay, we need to check the log file for this. So there is a log file. This is a log file. So as we see here, for the command 03, that is the read command, we are getting the what we see in the location 1 2 3 1F 5 6 7 8. For the fast read we are getting the same result. For the BB also we are getting the same result. So from this log file we can say that it is a verified read process for the QSPI as well. Okay, in next video we are going to have the device related commands, that is like erase or read ID, like that. In that we check the waveforms, how we can check that waveforms transitions in that panel. Okay, because there are lots of signals, so and already time is about 40 minutes, so it is better to have the discussion in next video. Okay, thank you, and please subscribe my channel and share, like, and support me. Thank you. Bye.